Okay, welcome to the recitation. Today is Hank on debugging. And for those new to this, you may not appreciate why you need this, but other names for this class is how to almost make anything and how to break almost anything. You're going to make many different things that don't work. And the challenge is it's just not clear. Is that high-level software? Is it low-level software? Is it electronic? Is it electrical? There are many ways, many things that can go wrong. Done wrong, it's just a miserable mess. Done right, it's a fun puzzle. And so this is Hank's introduction to the fun puzzle. Go ahead, Hank.
Hi all. So yeah, I agree with you. So debugging is for me. Also, it's fun because in the end, you try to make stuff work and you try to understand why. And it's really like here on this T-shirt, being a detective in a crime movie where you're also the murderer. So it's fun, believe me. So these are the topics we're going to cover. And with me, I mean me and Nicholas. Nicholas from Fab Academy Guru in Belgium. So debugging. So it's about finding why something isn't working. And the problem is that you often know you don't know where to start. And so you have because you made something that's supposed to do something and then it doesn't work. So how do you understand? How do you start to investigate where it goes wrong? And so the best thing to do is to divide it into pieces. So here you have this nice stair. So first, of course, try it again. Try searching on Google for others who have the same problem. But also isolate problem, because you have you made a board that you maybe could program, but then the LED is not blinking. So the programming part of the board is not the problem. The second part of the board is the problem. And it can either be a software problem and it could be a hardware problem. So you have to investigate further. You unpack some debugging tools and start researching. And then here at the end it says, my board is completely wrong, so then you have to start again. So what's important for debugging is that you know what's going on. So what you did till the problem arises. So what's happening, what's the environment, what are you doing, what are the results? And then you have to read it over, because by writing the problem down and by reading it again, you often discover where the problem is. It might be that you programmed the wrong pin to power an LED, for instance. So try to narrow your problem down, because you don't want to end up in something like this. So this is a very nice and famous problem. So when you start debugging, so you're in a panic, you're in a hurry, and you topple over other things that aren't a problem. So don't panic. Narrow down the problem. So, like I said, so reduce the problem. The first thing you do always is a visual check. So look for traces. Look for the points you soldered. Look if all the components are soldered the right way on the board. And for that, so often it's a good idea to use a microscope. So in this picture you see the legs of a tiny. So when you look at them without a microscope, so they looked okay. But when you look with a microscope, you can see that they are not soldered together at all. So first, I saw this visual check. The next thing that's so might be a problem of the past, but it isn't if you still use the SUMD or the 80 tiny boards. Look if you have put them together also in the right order, so that you have both the programmer and the PCB connected, powered on. Then if it's not, so if you still can't find the problem, so narrow it down. So isolate the problem. Here you have a serial, SUMD serial board. First thing you can check if you get the right voltage. That's the parts that are in the orange squares. Then if you can't program a microcontroller, it's probably one of the solder points that you see here in the orange part. So this means it's receiving enough power, so it's receiving the power, the powering is okay. Then the next problem might be here. And also by my experience, and you can say it over and over again, people tend to switch the microcontroller. So that they turn it halfway and solder it. And so that's a very common problem. If you can program the board, but if you can't read serial, if you don't receive serial information, the problem might be located also between the microcontroller and the UPDI pins, or the FTDI pins in this case. Sorry. So narrowing down the problem also saves you a lot of time. So try them all and do it also in a logical order. So first look if the board is powered, because when it's not powered, it's not doing anything. Then look if you can access the microcontroller. And so if you can access the microcontroller, so look further. So to narrow down problems, so one of the most useful instruments in the lab will be a multimeter. So multimeter you have in all kinds of sizes and functionalities. So this one is a very small one, but it's very helpful. So in my lab, it's used a lot. It's used more than advanced multimeters like this. So they are okay, but they're harder to operate. or even these ones. So nice digital one. And for this multimeter, the most common use also things is measuring continuity. So test the power supply to power pins continuity, and then check fuses, diodes, orientation, find short circuits, shorted circuits, and also at the end also track all the traces if they are connected. Measuring the voltage, you do it parallel, so check the cabling, that you have the right orientation. Always select the maximum ratings in order to not burn down your components. The power supply independence, you have to select it. Look for the ground and the VCC loop. What's here? So what can happen is nothing. So meaning you have somewhere you have a short. So meaning nothing. So means by checking continuity that you hear a beep constantly, and we will see it later. When the voltage is low, you get an unreliable board. When you have too much voltage, you may damage components on your board, like zener diodes and so on. Then, so it's a very useful tool and you should learn to use it. So it's so it can help you a lot. Here we have an example of the multimeter that checks continuity in the first place. So you check if the traces are connected to each other. You also check for the other islands if there are no shorts. So, although this is not so nice motherboard, and here also we check a capacitor. And you have to, so this is the capacitor settings. Now we are checking a diode. An LED is a diode, and because you send a small amount of power, so the LED will light up. So in this way, you can check the orientation of the LED. So when you look here, so the red pin, which is VCC, will be on the right side. The ground will be on the left side. The other thing you can measure is a voltage drop. So power on your board and activate what you've programmed and see how the voltage behaves.
Yeah.
You push the button, so you see that voltage is dropping down. And sometimes the voltage drop may be enough to make your board completely unreliable. The other tool we can use is a logic analyzer. So you have very cheap ones, you have very expensive ones. So this is a logic analyzer from, I think it's from Amazon or AliExpress. it's only costing $10 something. Then it's an 8-channel logic analyzer. This one is same. It's a 16-channel logic analyzer. And what you can do with a logic analyzer is reading digital signals. So when you combine them, put them on the board in the right way, you can intercept communication, for instance, on the serial, but also UART, I2C, SPI, one-wire, PWM. You can measure the timing between signals. And so these ones are connected, you connect through USB to your computer. So, so in this case, I use PulseView, which is open source software. And you can see in this case that I'm intercepting serial communication. And it's doing this by receiving. So this is signal you get in. And what it does also is to translate it automatically when you select the serial protocol into the text that's sent between the microcontroller and your computer. So here we have the detail. Oh yeah, but it's also, so those components are very cheap. You might want to invest a little into these hooks. So these hooks, so these, for instance, they are very good. You also have hooks that are very cheap, but very reliable, hard to put legs of microcontrollers to connect to legs of microcontrollers. So here you see a serial board connected to this 16-pin logic analyzer. And you see the bits coming in. You see that it's automatically translated. So this was going too fast. So on the upper part, you see what I typed. And then on the second, this part, you see the echo. You see it connected to the legs on the microcontroller itself. And here you see the translation of the bits into characters. So these are the links to the logic analyzers in the hooks, the micro hooks of DigiKey. Then, so Neil also mentioned in class, so you have this small logic analyzers from Miniware. They are very helpful and you can use them without a computer. So they have a screen where you can see it all. This logic analyzer itself, it has because it's open hardware. Many people made alternative firmwares for it, so you can measure a lot of other stuff. I can look if I can show it. So here you see all the programs that you can run. So with this alternative firmware, So it's I2C communication, for instance. It's so it's a lot. Okay. Okay, then now I hand over to Nicholas to continue.
So one other useful tool we can have in a lab is an oscilloscope that you can see. Yeah, next slide. Basically, has a very fast multimeter. On a multimeter, you can measure, for example, a voltage, but you will be able to see only a very slowly varying voltage. So you can measure 3.3 volts that will remain at 3.3 volts, but you won't see the very fast happening phenomena. So an oscilloscope basically is a very fast multimeter, or is the analog version of what Hank just did present, that was the logical analyzer. So the very, very fast sampling multimeter, we have a black square, yeah, okay. It can go from megahertz to gigahertz, so you can really capture very highly dynamic phenomena. There is a lot of functions on it. You can use triggers to watch at specific times when your signal goes from high to low, for example, and you really want to capture the moment your signals go from high to low. So you can configure a trigger. You can see in very wide space of time or very narrow space of time. It has a lot of analysis capabilities, but the price to pay is that usually it's very expensive tool compared to the logical analyzer or very basic multimeter. And also you have only a few channels, from one on the very basic one to 4 channels, usually not more. So because it's an expensive tool, if you need just to sample at quite high rate, but reasonable at, I mean, several thousands of samples by seconds, you can use actually a sound card, because that's what a sound card does. It just converts tensions and voltage to numbers. So you can use a sound card as an oscilloscope, but that's a very basic one. Next slide. We have to give credit to Doa for the video, because previous year we were giving this lecture with Doa, Quentin, and Hank. So what Doa is here is slow phenomena. She will just connect. Yeah, you can make it run, Hank. She will just connect the ground as a reference, and then she will connect the probe to the LED. So you can see actually the LED blinking. Actually, LED blinking is a very slow phenomena in electronic world. So you will see on the screen the signal going from low to high, which is actually not a very common use of an oscilloscope. What is already quite interesting, if you look very closely, is you can see already small spikes when the signal goes up on low, and you will never catch it with something slower as a multimeter. Okay, next slide. Here is a very common situation you can have when you have your voltage regulator on a circuit and you don't put decoupling capacitor. You can have stability issues. On the top, on the video, you can see a circuit without decoupling capacitor. On the bottom, you can see it with decoupling capacitor. Actually, if you have noise in your signal that will power, for example, your chip, and at some point the voltage really shortly goes under a given voltage, you can have your board that will be reset, and you will never catch it with a voltage meter, with a multimeter. So only with an oscilloscope you can catch it. Next slide. Hank? Yeah. Another example is when you push a button. It's not very obvious on the video, but I'll show it with a fixed image after that. You can see what actually is happening when you push the button, and then you relay the button, so you can see really the signal going low and then going high, and then you can really stop the time and start zooming on what's happening in between when you press and release the button. And why you can be sometimes it can be sometimes useful to see that. Maybe you can already go to next slide, Hank, for time management. That's what it actually looks like when you press a button. You think that you're actually only pressing the button, and what your chip will see is only the signal going from high to low, but actually you have a really mechanical effect of your pin bouncing on the metal. And so if you look really closely in short period of time, you will see that during 2, 3, 4, 5 milliseconds, you have bouncing signals, and it can lead to totally ununderstandable phenomena if you don't look closely at what's actually happening. But I'll talk a little bit more about that after, which is a very common problem when you start with playing with buttons and microcontrollers that are fast enough to catch actually those kind of phenomena. Next slide. Yeah, with an oscilloscope, as I said, you can measure things. So you can really measure the different voltage between different signals. You can also measure the time between two phenomena, and that's what Dua is showing. So she just pressed the button, release it, and she can measure exactly how much time passes between first and second signal. You can do it, push button is a very rough example. You can do it with very short signal that happens during micro or even nanoseconds, so that you can actually catch and measure quite precisely. Okay, next slide. Another stuff that is cool to have, actually we should have talked about the Hank and mine. We have some suitcase. I really take them during my holidays. I put it under the seat in the car, and I have like a mini lab in my car. And that's a really good stuff. PineSil is solder iron that you can connect on a USB-C, and that will hit from USB-C power. There is also, and PineSil I think is from Pine64, which is a group of open hardware hackers. So they produce quite cheap, actually, but still efficient hardware. There is an equivalent, which is a TS480P produced by SenseSmart, I think. That's a really handy tool to have in your suitcase. Next slide. Hank, if you can. Yeah. Another stuff that is handy to have in your suitcase is a DPS 3005, which is basically a DC-DC converter. So you can put any, as long as the power is enough, voltage in it, and you can select a voltage and current that the device will be able to provide to your circuits to test under really lab conditions. So you can see that the device is quite small. You can plug it in an USB or a battery or anything. It's a very handy tool to have in your box too. You can even connect it to a computer to actually measure what was the actual voltage and current you did deliver while you were testing things. So yeah, it's part of your mini lab. So now, what can go wrong when you're actually making your board and trying to flash it? So the first note is that, yeah, this year we decided to go to the UF2 new bootloaders that are actually, if I'm right, they are made into the factory, so you can't really break your chip anymore. But before that, and that's the case of a lot of components, and we are still using SAMD in Fab Academy and ATtiny. You have first to flash your board, to put your program into your board, which is a little bit less straightforward than in the RP2040 that we now are using. Next slide. So if you're using ARM chips, which is basically the SAMD for the Fab Academy, you have to talk to them with the SWD programmer. So to send the program to the chip, you actually have to use a special device, which is a programmer. You can even make one. You can program a board to be a programmer, and then you have to then push your code into your chip. So we are showing here how to do it with eDBG, which is a tool which is available under the three platforms. You can do it command line, but no, actually, I think Quentin did add it to the Arduino library is maintaining for the ARM processor. So you can do it directly inside Arduino. But here we are showing you how to do it. A very common way of working with ARM processor that actually can use USB is you push a small piece of code inside your chip, which is called a bootloader. I think Neil already explained that, which is a small piece of code that will just enable your chip to communicate with your computer through serial USB. And then when you need to push a new program, you will just send it over the USB. But that requires a small code to be first put into your chip, which is done with EDBG, even if you do it with Arduino, actually, and under it's EDBG working. Next slide. Previous slide. For this, you need, so SWD, if you can go one or two slides before, even one more. For this, you need several lines. You need to push a data line. You have a clock line, which is telling your chip, now take a data, now take a data, now take a data, and there is the reset pin. So it requires at least 3 wires from your programmer to your board, and even a fourth, which is the ground. So at least 4 wires. Usually connectors are 10-pin connectors. But we sometimes use 4 small pins connector in Fab Academy, 2x2 small connectors to connect it. So it's already 3 wires at least for the signal to be sent to your board. And why I'm saying that is that another family we use in Fab Academy is ATtiny, which use a fairly new protocol for programming and even for debugging, actually. Microcontrollers, which is a UPDI, which is basically a sort of serial connection UART, but which is used in what we call half duplex. So talking on only one line from one side to other. So for this, to program ATtiny, all you need is serial converter that will just output a TX and RX signal, which is to listen to and to write to, and you can connect them together with a small resistor. Use a 4.7K resistor, but any between 1.5 and 10K will work. The ID is done, RX is just listening what's happening, TX is speaking, and you need UPDI to be able to speak over your TX. So when TX is trying to speak and UPDI is just listening, TX will win. And when UPDI will start speaking, she will be the louder, and it will take the line. So you can connect them with a small resistor. It will also work with a small diode, actually. So one of the big advantages of UPDI is you can use only one pin. So you don't need to preserve too much pins on your board to program your chip. You can also use the bootloader trick, but usually we use it on smaller pins. And as the spinners are smaller, you avoid to use that part of the program to put a bootloader in. Next slide. So you can do it command line with the PyMCU prog, which is a Python program to send it. But once more, it was implemented in Arduino thanks to Spence, that they spend quite a long time to make it feasible. So you can now do it all in Arduino. Next slide. Okay, now a small piece about in-circuit and on-chip debugging. When you want to understand what's happening actually in a circuit, you have to watch at some things that are happening inside your chip, but you can see nothing. So one way to do it, which is the more advanced one, is to connect a programmer and to talk with the chip while it's running. And you can set up breakpoints. You can say, when you come to this line, you stop it and you just send to the programmer what's inside your variables, what's inside your memory, and you stop executing the code and you just send it to computer. And that's called what's in-chip debugging. You can use an Etmerize for that. And it can be done with OpenOCD. Next slide, please. Yes, you can do it with OpenOCD, which is a quite advanced tool and quite difficult to put hands in. So I won't go into too much details, but I put you a link about a course we gave for a bootcamp with Quentin from Fab Academy Guru, and so you can have a look at the link. But we explain a little bit how to use OpenOCD to debug, like really the hardware in command line your chip to look what's actually happening inside. Next slide. Okay, Nate did ask us to give some explanation about how to do it in Arduino board. Hank did had a look this morning, but I think he didn't succeed, and Neil either, as I understand. So it should be feasible with Arduino, but we still don't know exactly how. But there is something even simpler. I'll show you, I think, on the next slide. Oh, no, Hank, want to present something? Oh, no, you don't want. Okay, so next slide.
No, so this is ESP tool. You can use ESP tool with ESP32 C3 shell boards. And it's also sometimes it's unclear in what state your shell board is. And with this ESP tool, so you can see what's happening. A very common problem I noticed is that you have communication problems. That usually means that there's more than one connection. Yeah, there's also another piece of software that's occupying the serial communication. Another thing, and that's shown here, is that you use the wrong chipset. So that was it about ESP2.
So these were for more advanced tool when you want to do real debugging the hardware. But one way I do it most of the time, actually, it's fairly rare that I actually use the real debugging tools, is to put some message in your code. Yeah, next slide. A message can be just a LED blinking saying, I'm in that part of the loop, so yeah, hello world, I'm blinking, I'm here. But what you can do is send like real messages through your serial or serial USB. So it's just a trick to put so small pieces of code, and I usually do it with a define. I just define to 1, and so I can put this to 1 or 0 to enter a sort of debug mode. And so I call it explicitly debug mode, and I compile my code in a debug mode. And if I don't want that debug mode and I want my board to work normally, I just put it to 0 and all the messages disappear. So the trick is just to send messages through your USB or your serial communication to see what's actually inside one variable. For example, here I show a very small and handy piece of code, which is you will serial print debug, my value equal, and then you send the actual value, which is stored in my val variable. And so you can actually read what's inside your chip without any specific device or any specific programmer or something. It requires actually your basic code to work. So it means that you have to be able to have a serial communication with your board. But that's not really the way I work most of the time. Yes, next slide. Yeah, one very common problem you will have with your boards when you try to program them, especially for ARM, SAMD families. The first thing is that you have to make sure that it can communicate through USB. As I just said, if you want to send some serial message, for example, you have to make sure that your board is actually detected by your system. So I just showed some very small command to show how to do it under Linux. It should work also under Mac. You just list your USB devices and then you plug your device in, and you just check that when you relist all your USB device, you find one more device. In Windows, you will hear a small sound popping. You can see it in hardware. Now I will check. Next slide. You can do it dynamically with dmessage, which actually is a log of what's happening inside your system in Linux. If you launch it with a W, you will see what actually did happen before. Then you plug your board in and up. You see that there is a new device that just appeared. And if you removed it, you can see that the device just disappeared and was disconnected. So really basic and handy stuff to see that you can already have some sort of communication with your board, that the board is already recognized by the system. So it means that the bootloader was properly flashed and that your board is working properly. It doesn't mean that your code will work properly, but at least you can communicate with your board. Next slide. Yeah, radio communication is a bit more tricky stuff because it requires some knowledge about basic mathematics or physics, or you just have to follow a small tutorial. But next slide, with a very simple tool, which is a DVB-T. DVB-T is just a USB key used to watch TV or listen to the radio. It's a pretty new device. It's just something that is able to measure the electromagnetic field in very high speed and just send it through the USB, and it will let your computer do all the math to actually catch the frequency and the radio signal. But you can use it actually to catch radio frequencies that are just happening in the air, and you can put it at a given frequency and then transform all the information to watch actually what's happening in the air. It can be really useful, for example, if you have a small remote that is already made in factory or something, and you don't want to open it and to reverse engineer it. You just push the button and you can listen to what's actually happening in the air. And it can go from kilohertz to gigahertz. Usually they won't go that high, so you won't be able to catch Bluetooth or Wi-Fi, which is a little bit too high, 2.4 to 5 gigahertz. But unless you're working under gigahertz, for example, with 433 megahertz, which is very common for radio remotes, you can watch your signal that way. I show in small video, next slide, how to do it. We won't let the whole video go because I think it's more than 4 minutes. So maybe Hank, you can advance a little bit in the video. So it works a little bit like mods. You have to connect modules to do mathematical and computing operations. You can go a little bit further, but you see with some small boxes, you can connect things together and transform that very raw signal into something more useful to debug your radio communication. You can go a little bit further, Hank. Until we get like nice images. So what I'm doing is I'm transforming the waves, which is represented as complex numbers, to real numbers, and then I put into a beautiful. Hank, you can go a little bit further until we get like clear signal. Even further, Okay, here you can see what's your signal, and when I press the button, you can see that the frequency at 433 megahertz is showing up. And then with this, I will go, can go still a little bit further. I'm doing some more operations that will let actually see and read the signal more clearly. So now you can see the signal on the bottom line, and on the upper line you can see the history, and then you can see already the frame that is going on. And if you go a little bit further yet, you can see it like a little bit like a logical analyzer. You can see the pulses, and which are basically 1 and 0. A little bit further, yet further. Video is quite long because I show it all extensively. So we'll have a look. And then you can really see your 1 and 0 just by software. Actually, I just plug that USB, which is I think $10 or $20 or something, which is not normally done to just watch TV or radio, but you can use it as a very handy tool for your radio communication. A little bit more advanced use of this kind of DVB-T. I think that's it for the tools. Hank?
Yeah, this is all we have. I think it's more than enough. So what you've seen as a lot of ways how you can debug stuff you make and it doesn't work. So if you have questions, put them in chat or ask them here in the video.
Any questions? Nice tour, Hank Nicholas. Just a few general thoughts. You can debug from the bottom up by having separate things you know that work and putting them together, or by the top down, knocking things out in the system. But it's important to think about that strategy of bottom up or top down. I would approach with a checklist. You know, when I come into a lab and a student says the board doesn't work, the first thing is just look at it and stare at it and see if anything is wrong. Then make sure it's getting power. And I'd say the most interesting debugging puzzles are ones where you need to look beyond what you see to a non-obvious thing. Like one of the most interesting historical examples was the optical properties of semiconductors were discovered at Bell Labs because they were measuring early semiconductors and there was an oscillation, and they spent endless amounts of time trying to figure out why their circuit wasn't stable, was oscillating, until somebody finally looked up and realized there was a fan turning. And there was a shadow from the fan. And a lot of debugging has that character that you're focused on something to try to explain it, but it's coming from somewhere completely unrelated.
Another thing you should be careful about is that when you're measuring things, you're actually modifying your system. So sometimes if you, a stupid example, if you try to test continuity from a chip and you push it on the small pin, you're actually pushing the pin on the board and you can connect it when you are measuring, and then you release and the circuit stops working, and when you measure it, it works because you are pushing on your system. Or sometimes if you want to measure something with a touchpad or something and you put an instrument on it, you modify actually your circuit. So be careful and be aware of what you're actually modifying when you are doing your test. It can be an instrument.
Yeah. Jason is asking what to buy to start. Actually, I think what I would get is, at this point, there are cute little pocket $100 oscilloscopes. And even the bench ones have come down to a few $100s. So I would, if I had one thing, I would get that, because you can use that to do what the multimeter does. You can use that to begin logic analysis. And so I would probably start with that. Is a little bench or pocket oscilloscope to start. Then from there, I would probably get the multimeter, and those are very cheap. And then after that, the logic analyzer. Yeah, I see Kyle Pierre showing his little one. Okay, any other questions, comments? Oh, yeah, so Jason, absolutely a soldering iron. That this was just the debugging tools. I would absolutely get, at this point, a little hot air, so you can get a station that's both a programmable temperature soldering iron that heats and cools quickly, and also has a hot air station. And we'll be covering, that's right, we haven't done this yet because we're going in this flipped order. On Wednesday, I'll be talking about soldering, and a lot of the processes now need hot air reflow. So I would get a hot air So yeah, Adrian's showing his little USB pencil soldering iron. That's the first thing I would get. But pretty quickly I would get either a hot air gun or I like the little stations that's both soldering and hot air. And I'll be going over that this week. Okay. Yeah, so some of this may sound abstract. It'll become real when you start making things that break, and you'll come back and appreciate, you know, everything Hank and Nicholas told you is the result of pain. Every lesson has been some afternoon sunk trying to solve some problem.
Yeah, but so fixing your first board is as exciting as your first blinking LED. So
it really can be ecstatic when you solve a really hard puzzle. Yeah, I mean, yeah, just some like a classic really difficult puzzle is a race condition, is where you have something that depends on the order that it happens, and sometimes it's faster and sometimes it's slower, and that depends on the code execution. And so it's just like flipping a coin to try to debug it. Another one that can be really hard is Nicholas mentioned, if there's fluctuations in the power supply, your code can trigger something that happens that then consumes power, that makes a glitch, that then impacts the code. And so it looks like a software problem, but it's actually a power supply problem. Yeah, these are kind of problems that don't have a clear symptom, and when you debug, it doesn't make sense because it's sort of random, it's not predictable, and things that don't make sense actually are a clue to the type of problem.
Yeah, well, I just wrote in chat, the fact it's random is already an info. If you can repeat your problem each time, it's already an info that you can use for debugging. I didn't show it extensively, but the button is a very classical problem. If you try to make some button that will light on or light off a LED and you don't debounce it, you will push the button, and sometimes it will work and sometimes it won't work, because it will just depend on how many bounce your chip will catch. And sometimes it will be an even number, sometimes an odd number, and it will light or not light your LED. And yeah, it looks random, but if you look closely to so what's happening, it's not that random.
Oh yeah, and right, another lesson is there's a probability of fixing something wrong, and the number of things simultaneously wrong, you multiply those. So I think the most I've ever had to debug simultaneously is something wasn't working and it turns out 3 different things were wrong. And you're trying to find one cause, and you might realize there's 2 things wrong, and it's really hard when in fact 3 different things were going wrong at the same time to explain it. That's one of the reasons why I really argue for modularity. When a big system is going wrong, it's hard to tell. It's much easier to have isolated things. But yeah, a really nasty thing is when you're debugging and you're looking for a cause, but there's more than one cause. And so you can fix either cause separately, but it doesn't do it. You have to realize multiple things are going wrong at the same time.
Yeah, but the problem is sometimes you do the contrary. There is only one cause and you're modifying something else and you're creating a new cause, not fixing the first one. So always go back to your first situation. For that, use Git and so on. But yeah, try not to, as Hank showed with the guy panicking in the bricks, not to create more damage than you already have.
Yeah, and yeah, one more lesson is when you're really stumped, just do stuff. You need phenomenology. At the boot camp in Kerala, ARM processors weren't working, and I just stumbled across, I forget how it happened, but if you touch a lead with a tweezers just in your hand, then it would work. And that was a hint that I was adding capacitance, and we went all the way back to the vendor, and it turns out that there was a slowly rising power reset issue. But you can't debug without phenomenology. You can't do it by introspection. Yeah, Hank's making a note about debugging the students that debug. There's a subset of students who just are miserable because each problem, you know, is like a personal failing. And then the ones who succeed appreciate the hunt, appreciate the challenge. Okay, if there's no more questions, we're up to 10 o'clock. So thank you, Hank and Nicholas. Happy debugging, and we will start making electronics on Wednesday.
Ciao.